Okay, so hi everyone, I'm Vincent from the AQG-B team, or the Exale as we're now called. So the name has changed last month, so it's very new for us too, but so many changes in the name, but still the same team and same people working on the project. And so I'll be talking to you about basically what we've been doing on developing the AQG in the frame of the project. And I am giving this presentation on behalf of Laura, who did most of the work, but who could not be here today. So the main target for us in the frame of this project was basically to turn the absolute quantum gravimeter from a lab version, which existed in 2018, something like that, into a field version, adapt it to the specificities of volcano operation, in particular in terms of vibration. And then finally, to show that the instrument could be operated on volcano and provide some relevant data for volcano monitoring. So the project timeline for us, so the design started in October 2018, so about 4 years ago. We started to integrate the instruments, so putting all the pieces together about a year later. Lab tests early 2020, so that means characterizing the instrument in the lab in friendly conditions before going outdoors. Then it was installed on Mount Etna in early August 2020. It stayed there and well, still there, except for 2 months this year where we took it back to Talence for a system upgrade before putting the instrument back up at PDN. So just a quick reminder of how the instruments work. So it's an absolute gravimeter. Most of you might be familiar with the FG5s, where there's a corner cube that's being dropped. So here, instead of dropping the mirror, we're dropping a cloud of atoms. So we start by shining a laser into a specific pyramid reflector, and this allows us to trap some atoms. So we have like a ball of atoms under vacuum. And this ball, the atoms are cold, so it means that they're very slow. So basically, we have a cloud of atoms that's not expanding in time, at least with respect to the time of the experiment. So then we turn off the lasers, and we have this little cloud of atoms, which is in free fall. And we measure the acceleration while it's falling by applying a series of laser pulses, and then performing a fluorescence measurement. And with this, we can get a precise knowledge of acceleration. So I won't go into the details of the physics today, just to tell you how it's working so that I can show you how the instrument looks like. So when the project started, the instruments looked like that. So this was like the AQG-A, so the first version dedicated to a lab or at least a controlled environment. So it was not at all hardened. So it was for indoor use. They could work in a limited temperature range, and many cables. You can't see them on the picture, but this is a picture of the back of the instrument. And I think there's like over 50 connectors. Not all of them you have to plug and unplug when you set up the instrument, but still there is a significant amount of them you have to install when setting up the instrument. The AQG-B on the right is dedicated for field use. So the temperature range has been extended. We've put some temperature stabilization in there. We've greatly reduced the number of connectors. All the connectors of the instrument are visible in the picture. So you see there's like 10, and they're hardened connectors, so easier to use. We've improved all the electronics to make it less power consuming, to make it easier for us to assemble, easier to characterize, and so on. And also we've worked on the modules to make sure that each of the boxes you have to carry are less than 40 kilos, so that they can be carried by 2 people on the field in a rather convenient way. So, and I have to thank all my colleagues that there's been a lot of work by all the people in the electronics, in the mechanics, in the optics, working on going from the first version to this field version. So the main features of the field AQG. So we've worked a lot on the integration. So basically everything is made in-house. We design all the electronics, all the optics, all the software, and we put a lot of monitoring. So we have access to hundreds of parameters in the system to make sure that we can check that everything is running well. of course, we have to do this and keep in mind that the users are not quantum physicists. So a lot of the work we do is like thinking, how are the users going to understand what we're doing? And so we're trying to make the setup, like the system simple to operate, easy to set up. And also the remote operation is very convenient because then it means we can help people remotely. And this has been quite useful for the Newton-G project. And of course, we have to do all this without sacrificing on performance. And here the target resolution is 1 microgauss for the long-term stability of the device. We had to adapt for Newton-G to adapt some features of the instrument, and in particular dealing with ground vibration, because the level of vibration is very high on the summit area of Mount Etna, especially in the range between around a few hertz. You see on the spectra here in green is basically the spectrum we have here in Talence, and here there's a big bump, which is a very characteristic of what we've seen from Mount Etna, and which we usually don't get in quiet places. And this was not suited to the way we compensated vibration until then. So the way it works, if we don't do anything, because the atoms are falling, if the system is shaking, basically the information we get in the end is G plus a contribution due to vibration, which creates some noise on the measurement. So what we have to do is we attach an accelerometer to the vacuum chamber, we record the acceleration, and we do some real-time processing so that we can derive this vibration contribution, and we can apply a correction on the lasers to take it out. So this is done in real time at each cycle. Every time we drop the atoms, we can apply this correction. And until Newton-G, we did this with an accelerometer. The problem is, it was a nanometrics Titan. The problem is this accelerometer has a DC component, which we filter out because obviously what we want is the atoms to give the DC component. And it's quite hard to do this in a nice way. And typically the filters we used would create some problems in this spectral domain. So in the frame of Newton-G, we performed some simulations which showed that the accelerometer would not work well. And so we went for a nanometrics seismometer, which is a broadband seismometer, which has an integrated high-pass filter around 100 seconds. And so this part of the spectrum is measured very well. So that was a significant change we implemented during this project. So the instrument was set up at PDN in July 2020 or early August, I'm not sure. In the observatory. Luckily, we had provided a very long cable and fiber optics, because basically when people went up there, the racks of the laser and electronics basically didn't go down the staircase. The staircase was too narrow. So we could set up the sensor head in the basement on a dedicated pillar and leave the laser system on the ground floor. And it turned out that the conditions were quite challenging, of course, because of vibration. So I've talked about that. There's been many eruptions creating a lot of vibration. Temperature changes were also an issue in this project. So there is obviously no heating in the observatory, so it can get quite cold in the winter. Something that we are not anticipating is the corrosion due to the acid gases on the volcano. So this is a picture from this year when we went back to the volcano to bring the instrument back down. There was a lot of rust and corrosion on the connectors.
Not some.
Of course, the access is difficult. The first time they brought the instrument in the truck, I think Jean was pretty scared that something would break. And then if you have to repair up there, it means you have to take some time for Alfio to go up there and do the repair. Of course, in the winter, it's nearly impossible. And we had many problems with the off-grid power supply at the Pizzidineri Observatory, which created many failures, many interruptions in the data acquisition. So I'm going to show you some results, but Daniele will talk about the interest for geophysics. So I'm just going to highlight the instrument perspectives here. So the first thing was dealing with vibrations. So this is like a spectrogram during 4 months of 2020. And you see that we had both periods where the volcano was very quiet here, and here was a lot more amplitude in the noise. And you see the difference here in this low frequency regime, for example, in the this few second range, the difference is quite significant. But in both cases, the gravimeter was able to record data with sensitivities which are compatible with what we had done with expected with simulations. So we were pretty happy with the seismometer implementation, and that we could record good quality data despite the high level of vibration. So this is the time series from the installation in 2020 up to November 2021. Just to show you the kind of things we had to go through. So you can see in the first part, there is many gaps in the data. This is not because of the AQG having problems, it's because of the power supply having problems. Luckily, a significant portion of the times we were able to restart the instrument remotely. Only a couple of times it was necessary to go up there. And then, of course, at some point, the power supply failed and there was too much snow for the site to be accessible. So the instrument was left completely unattended for 6 months in the winter. So that means there is no power to the lasers, no heating. And maybe the thing that was worrying us the most is there was no ion pump. So there was nothing maintaining the vacuum, actively maintaining the vacuum. So we were kind of worried and, not knowing what to expect when we could restart the instrument. But the restart was okay in May 2021. Actually, just within a few hours, the instrument was up and running again, which we were very happy about. And it was actually again the case this year. Everything was cut off during winter and we could restart it without any problem. And then the last part of the time series, there's less gaps because the power supply had been improved. And there have been many lava fountain episodes. And so the feedback we get from Daniele and his team is that the instrument was behaving well compared to iGraphs, for example, during these periods. So again, this is something that we're happy about. Oops. So to sum up on the data availability from the AQG, it was installed in August 2020, 2 main data acquisition periods, August to December 2020, and then May to December 2021. During the winter, it was not working, but this is not our fault, basically. And then we took it back to Talence this year to upgrade the system before the end of the project. And then it was sent back to Etna in July this year, a couple of weeks to get it running correctly. And then now it's acquiring data again. And overall, there have been a few issues with the AQG, but most of them were sorted remotely with us accessing the instruments when it was necessary, and we could solve most of the problems. So as I said, the system was upgraded this year. The idea is basically to implement new developments that we've been working on here and to try and improve the performance and the stability of the device. It's upgrades that we had implemented on other instruments and that we wanted to put in this instrument. The main one when it comes to the measurement quality is putting an automatic system to align the laser beam. Until now, it was rigidly attached, so we would do the setup once in the lab and hope that it was stable enough on the very long term. We had done some tests and it was okay, but on the very long term, we experienced some small drifts. So now there is stepper motors, motors actually, that can realign the laser beam with sufficient accuracy to maintain the uncertainty below 1 microgal on this parameter. And the second thing we implemented is a UV LED. This basically helps to clean all the rubidium that gets absorbed on the windows of the vacuum chamber and improve the vacuum. So that's also something that we have implemented on all our instruments. And because when the instrument was here, we also performed like a general check of the system to make sure that there was no major problem, which was the case. The instrument was running well after 2 years in hard conditions and those 2 winters with no power. So that's something we were happy about. And also we were wondering, seeing the state of the connectors and all the corrosion, we were wondering what the inside of the system would look like. And it turned out that the packaging was sufficiently airtight and that everything inside was looking okay. So we didn't have to change any components or repair anything inside the system, despite the state of the connectors outside. And so now the AQG is back at PDN, it's up and running. This is just preliminary data. This is like 2 months of data. So the data is looking good. There's small variation of the order of like a few microgal, but like comparison with the iGraphs. And again, this is like completely preliminary data. There's been no processing, but all the instruments seem to see a decrease in gravity. So we are pretty confident that this is not related to the AQG, but rather to some geophysics. And so I'm coming to the conclusion of my presentation. So I think for us, Newton-G was a very fruitful project. We've been able to basically accelerate the development of the field version. It was something that was in our plans, that we had done some preliminary design, but with Newton-G, we were able to make this work. So that was a very, very useful project for us. And we've learned a lot dealing with vibrations, putting the instrument in harsh environments. That was really helpful for us. It was the first opportunity for us to test an AQG in really challenging conditions. Until now, the AQGs had been used more in observatory conditions. So putting it on a volcano was really an important experience for us, and getting all the feedback from the people from the consortium was great. We're happy that the signals are relevant for volcano monitoring, because of course that's the final target. And so Daniele will talk about this, I think, this afternoon. On the project management, luckily we managed to go through COVID without too much problems. Basically, because all our instruments can be operated remotely, and the AQG for Newton-G was already at a stage where there was no need for like a hardware interventions, so we could do all the testing remotely when we were in lockdown. So that was I think quite convenient, and we managed to like keep track with the schedule. And for some of us, we're happy to enjoy field trips to Catania and nice food. So it was a nice project from this perspective. And so yeah, I'd like to thank everyone. First, I'd like to thank all my colleagues who put a lot of effort into the project: electronics, the optics, mechanics, the software, all the physicists who've worked on characterizing all the AQGs and improving them, and especially Laura. All the partners from the Newton-G project. Has been very cool for us working with you all, so we're very happy about that. Thank you, Daniele, for running the project. That was really enjoyable. And yeah, thank you for your attention.